Okay, let's talk about the force of gravity, right? So the gravity is the weakest of the fundamental forces. Here's a picture of Sir Isaac, and this is before he, went on the weight reduction program. Either that, or when I changed the aspect ratio of these slides, it widened his picture, right? But anyway, this is the thing, right? And here's, of course, the story is that he's sitting under the tree, and the apple falls on his head, right? And at the moment the apple falls on his head, he looks up and sees the moon. Right? Now, at this time, we knew four things. We knew the distance that the apple is from the Earth's center. In fact, this was known since the Greeks, the Euclids did this. Geometry literally means to measure the Earth. And they did that by looking at the sun when it shone down a couple wells near the equator, right? So he knew that distance. He knew the distance that the apple falls in a second, which is, of course, that x is 1/2 at squared, right? Okay, so it's proportional to the acceleration, right? Okay. Then he knew the distance the moon is from the Earth's center. Okay, roughly. We had triangulated the moon, right? And at this point, we knew the distance it falls in a second. And I know you're going to say the moon is not falling, right? But if we look at it, let's say we look at it for some short interval of time, it actually falls some distance off of the straight line path that it would go. Okay. Now really, what's going on here is that there's a continual change going on with this velocity. And so Newton realized immediately that he had to invent calculus, right? He had to somehow figure out this continual change required something more intelligent than going, well, it looks like it falls some distance here. Calculus is a way to make that all work, really work, okay? And I think for some period of time, it's quite possible that Newton was the only one who knew how to do calculus, which is kind of an amazing thing, right? So basically, he concludes that there's this inverse square relationship, that if you double the distance, you cut the acceleration by a factor of 4, right? It doesn't doubling the distance doesn't cut it in half. It cuts it by an inverse square. Okay, if it's 3 times the distance away, it would be 1/9 the acceleration, right? And he comes up with this idea of universal gravity. And sorry, these circles are no longer circular. That had the same thing happen to his face too, right? Is that if we know this center to center distance, right, and we know the two masses, right, g is just some constant. So he comes up with this brilliant formula here, right? And by the way, this is pretty much common sense, right? We know that if we double the mass in the laboratory, that the weight of it doubles, right? We surmise that if the Earth's mass doubled but the radius stayed the same, that it would also double the force. The only cleverness is this inverse square, right? That it actually is an inverse square. And then there's some constant, and basically Newton didn't have the wherewithal to come up with what that was, because these forces are very, very small. If you have 1 kilogram and 1 kilogram and they're separated by a meter, this force turns out to be 6.67 times 10 to the minus 11th newtons, right? And then if you put the units on the thing, there it is, right? But, how do you possibly measure a force that small? And then, of course, the answer is you don't, okay? So we'll leave it up to Hank Cavendish, right? Who actually in 1798, right, determines the value of g with a very ingenious thing. He's got a sphere of lead mounted on a rod. You really can't see the rod here, but there's a little rod that mounts that on there. It's hanging from a fiber, right? When I did this in physics class, I think we used monofilament line, right? And then, here they show like a little ball on the end of a stick. These, I think, were actually fairly massive things on wheeled carts. They got them close, and if you get these guys close and you put another one right there, these guys attract each other. And this thing rotates the tiniest angle. Some little, whoops, that wasn't really an angle. Some tiny angle here that you can barely measure. So what they did was they shone a light on a mirror that was mounted to the rod. And if you move the mirror just a little bit, this light will move quite a distance on a far wall, right? Have you ever done that? Have you ever caught your watch in the sunlight and you get like a little shaft of light and you can very, very, delicately move that thing around with the slightest movement of your watch face, right? Anyway, he basically measures g and figures out that g must be 6.67, and I don't know, I can't remember what his value was, but he was really very close. I think when I did it in college, in first year physics, I got like 6, and we all clapped that 6 was very close to the 7 that this would round to, okay? Anyway, the units cancel. So let's do some examples here, right? So let's find the force of gravity between two normal objects that are just sitting around in our laboratory, right? So this, by the way, is like the world's heaviest stapler, but that's okay, maybe it's, right? So we're going to use our formula. So force is G m1 m2 over r squared. So that is 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. Now I know you're looking at those units going, that does not make sense, okay? But it will, you'll see, right? And then one of the masses is this guy, so 0.756 kilograms, right? And 0.341 kilograms, right? And then we're going to divide by 1.75, and don't forget to square this, right? I give a test on this, and I'm so disappointed because everybody doesn't square that. It's so sad. Okay. Now before we do this, right? Notice that the kilograms squared cancels both of those guys, and meters squared cancels meters squared. And these units are just, all those fancy units are just made up so that we get force in newtons. Okay. So this force is going to be in newtons, and the units of that are contrived. Now, I take my calculator. I'm going to do this. When you do this, you've got to go 6.67, right? You type it in 6.67 E minus 11, right? And that number on the TI-84s is like second comma. On my TI-86, it's just right there, and it has an EE on it. So find that. Find the little e. That's exponential. I don't know. Why is it EE? I don't know. Okay? So I'm going to go 6.67 E minus 11, 0.756. 0.341 divided by 1.75 squared. So that guy, and I'm going to go E minus 11. Whoops. Okay, times 0.756 times 0.341. A marker. That's a very heavy marker. It's made of steel. Okay, divided by 1.75. I need a lesson on what the actual mass of ordinary objects is. I'm getting a number. I'm getting 5.61 times 10 to the minus 12th newtons, right? This is an amazingly small force. This is why we don't notice it. Okay. Now some kids asked, okay, so would you ever notice that force? Well, we don't notice it because if they're sitting on a table, here's a marker and here's a stapler or something, right? The force of friction is much, much more than that. They would never overcome that. Even if it was a frictionless surface, the air currents would be stronger than that. But if we placed them in outer space, if that distance apart, and left them there, I think it takes about a day for that force of gravity acting inexorably and without opposition, right? It takes about a day for those guys to drift together and go thunk, right? So gravity's there. It's what collapses nebulas and gives birth to stars. All right. There's our first example. Let's do another example. What is the force of gravity between 1 kilogram mass and Earth? So here's Earth. Here's a 1 kilogram mass. This is not to scale, okay? Because if it were to scale, all right. So let's see. And then remember that we can't say that the distance separating them is 0 because the r is the center to center distance, right? So we got to use this distance, which essentially is just the radius of the Earth, a lot of meters, right? Okay, so I'm going to do the same thing. I'm going to go force is G m1 m2 over r squared. That's 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. Right, times our first mass is, we'll say it's that mass. It doesn't matter. Multiplication is communist. Oh, commutative. Okay. Let's see, and then our other mass is this guy, right? So it's 5.97 times 10 to the 24th kilograms, right? And then that is divided by 1. Let's see, this guy, 6.38 times 10 to the 6th meters, and then that is indeed squared, okay? And again, the meters squared cancels meters squared, kilograms cancels kilograms. We'll end up with newtons of force. Now, what do we expect? A 1 kilogram mass on the surface of the Earth, what does it weigh? I think we should know this from what we've done before. So let's just see what we get. All right, so it's recommending a change of batteries. Watch it die on me, 6.67 E minus 11. Okay, so what I type on my calculator is I go 6.67 e minus 11 times 1 times 5.97 e24. Now remember that e button is the second comma on my calculator, right? It's also called x, but it's also called 10 to the x on some calculators, right? Okay, and then I'm going to go divided by 6.38 e6 squared. Now this really does work. It doesn't square the 6 and then raise it to the 36. If that makes you uneasy, though, as you might be with a TI calculator, put parentheses around it. Okay, but you don't really need the parentheses. So I'm going to go times 1 times 5.97 e24, right, divided by 6.38 e6 squared. And I get 9.78. So about 9.8 newtons. Right? And of course, this is where this is our G, right, is 9.8 newtons per kilogram, right? Ta-da. So change the mass of the Earth, make it bigger, that gets bigger, make the radius of the Earth bigger, but don't change the mass, that gets smaller, right? Which is interesting, all right? Those are your examples. You should be able to do, as long as you can do this scientific notation, right? Use that exponent thing. As long as it looks like this in your calculator, you really are on track. And you're ready to try some of the examples that'll come after this.